So moving from 2D to 3D imaging, we have the computer tomography, what is called computer tomography, and the so-called full 3D tomography, which is now the best solution. So a tomographic image really generally needs something between 100 and 1,000 scans to produce the image. To store the multitude image and process the data, of course, you need a computer. You see how essentially it is the idea that this is a two-dimensional image that corresponds to a three-dimensional section of the patients, with the third dimension being the slide thickness, which is typically a few millimeters thick. So you go through a slice of the patient. Here you move the X-ray source, you move the detector, and eventually you end up with an image like that. Or if you go into the abdomen, you come out with a slice like that. And here you use different scans from different angles instead of moving through the patient. The spatial resolution we will see can be of the order of 1 millimeter, with the density discrimination better than 1%. However, now the present CT machines, all of them have a rotating X-ray source. This allows to scan the patient, which is located along the rotational axis from all sides and all angles. And the detectors is designed as a stationary ring, so you have ring detector around the patient, which receive the portion of the fanned X-ray beam. So you see here is the detector of this. This is how it looks like a modern CT machine. You see detectors are here, the patient couch is here, the image reconstruction unit is here, and here is how it looks like the image. You see, this will all rotate. So this is the source, this is the detector, and this is how it looks like from the front. Very fancy machine. So the projection here is calculated using this formula. Again, you recognize pretty much the scheme of the film detectors. So that's essentially, you can write the projection as mu x times x, where mu x is the summed attenuation coefficient of the different materials along the line x. So the attenuation coefficient corresponds directly to density of the body tissue, and so the projection corresponds to the density. Now, if you do a complete scan along different axes, the cross-sectional density along the slide has to be constructed using Fourier transformation. Now, the important thing here is that how do we characterize this attenuation coefficient of the pixels, essentially, because we have this pixel and we have to build these numbers. So each pixel, if we use 12 bits, each pixel has a value up to 4096, which corresponds to a level of gray. So if you wanted an attenuation, a black pixel will be completely means very little attenuation, and the white pixel will be very high attenuation. This number is called CT number or Hounsfield unit, and is expressed in this way. You see the CT number, the Hounsfield units, is 1000. The attenuation coefficient in the pixel minus water divided by water. So essentially, this is a way to normalize this CT scans unit in what is called Hounsfield units. It's called Hounsfield units because Hounsfield was the person who invented the CT and received the Nobel Prize for it. These are typical values of the Hounsfield units in CT. You see, in air, by definition here, in air, in water, it must be 0, you see, because in water, you will have this one, water minus water divided with water, so it's 0. But you see, in air, because the density of the air is approximately 1,000 times smaller than density of water, is about minus 1,000, and in the lung, which has a lot of air, is about minus 500. Then you see that goes up for different organs. You see in the muscles is somewhere in between 10 and 40, and in the bone can be between plus 700 and plus 3,000 for the dense bones. But you see that also, for example, also for the brain, you have substantially high levels. Of course, if you use contrast media, you can see also the soft tissue with relatively high. And the blood is also between plus 30 and plus 45. This is an example of a, let's say, a cutting edge machine, the new machine, the new CT scan from Toshiba, where the resolution now in 3D can be as low as 150 microns. So it's comparable to the resolution that you have in 2D radiography in the single pixel. Now you can have it in 3D. You can have a resolution around 150 microns. So it's really, it's an amazing machine now. These are examples, let's say, of the difference between conventional scanners, if you want, and Aquilon, which is a next generation CT scan, let's say, very modern. You see here for the abdomen, this is a standard CT, and this is a ultra high resolution CT. Please note that you get this without substantially increasing the dose, because this dose is 11 milligray and this dose is 12 milligray. And this is a lung where you see, I mean, the big difference when you go to the high resolution, you see how this tumor that is actually already visible here becomes now very well resolved when you go to very, very high density, high resolution. So the dose in CT scan is not negligible, as you say. I mean, we are in the order of milligray, but the problem is what is called the integral dose. You get an integral dose, which depends on many factors. You see, this integral dose depends on the area that you are irradiating, from the absorption coefficient, of course, and from the incident dose, say, from the skin dose, from the entrance dose. So this formula gives you a way to calculate the integral dose, starting from the surface dose and the characteristic of the penetration depth and the thickness of the sample and the absorption coefficient. This turns out to be for the skull, for example, where you have, this is a mu, sorry, it's not an m, it's 0.33 centimeters minus 1, an area of 256 square centimeter, 4.8 milligray. This turns out to be an integral dose of 3.7 joule. So you see the dimension of the integral dose is joule, is an energy. And this is a little bit complicated. Let's say it's not directly a dose, if you want. So you have to convert. But you see, it's in the order of the milligray anyway. Now, however, milligray can be dangerous if you assume that you make many scans, and if you look at the risk of cancer, Already in 2007, you see Brenner and Hall from Columbia University, they published a paper in New England Journal of Medicine making prediction based on a bomb survivors database. And they predict, you see, that one cancer in 1,000 head scans for child with less than 5 years, one cancer in 2,000 for adolescents, and one cancer in 500 abdominal or pelvic scans regardless of age. So these are numbers not so small if you think about, These are quite, because if you think of the amount of scans that are done, these are numbers not so small, but on the other hand, you can say, well, it will be very difficult to detect them. Well, very difficult, not so difficult apparently, because in UK, you see, this is in 2012, they made an epidemiological studies on about 176,000 children and adolescents. And you see a very nice dose response curve here for leukemia here. Even leukemia, you see, this is the bone marrow dose, and this is the brain dose, and you have a very nice relationship of leukemia and brain cancer for these people, meaning that, 2-3 head scans can triple the risk of brain cancer, and 5-10 head scans can triple the risk of leukemia. So it's, of course, you need many head scans to see an effect, because you have to go to relatively high doses. But this means that the CT has to be given with some rationale. Not every children that hit the head should have a CT. This study was very controversial because, it was the problem with this study that then medical doctors becomes afraid to make CT scans, and being afraid of giving CT scan, they can miss some important damage in the body that they will catch with the normal CT scans. And this is interesting. You see, the study that was published on British Journal of Cancer not so long after the first one. This is 2015. The original study was 2012. And this is a problem of seeing whether the study on cancer risk from CT scan are biased by indication, you see. And this is interesting because the problem here is that if you consider the excess relative risk for CNS tumor and you make the adjustment for prognostic factors, you see, for this predisposing factors, let's say. So essentially this means if you make a CT scan, generally you have a reason. So if you make the adjustment, you see that the excess relative risk declines quite substantially, you see, showing that, you see, for lymphoma, for example, here, a little bit less for leukemia. But so apparently this effect is not necessarily due to the fact that you make many CT scans. It's due to the fact that you have predisposing factors to leukemia or brain cancers, and these factors are those that eventually cause the cancers. Finally, dual energy CT. We have already seen dual energy radiography. For dual energy CT, you can simultaneously gather data from low and high kilovolt. This is particularly interesting for particle therapy, dual energy CT, because you remember that one problem was the range uncertainty, and there the problem is the conversion of the Hounsfield units into water equivalent path lengths. But if you use dual energy CT, you can actually get much more information on the normal tissue, so you can actually determine independently the electron density and the effective atomic number, and then you can calculate directly the water equivalent path length. So this this dual energy CT can help to diminish the problem of the range uncertainty. The other frontier now in X-ray is the so-called radiomics. Radiomics, generally what you do these days in the prognosis of the cancer, you take a CT scan, then you take a biopsy, then you look at the genome of the tumor, and then you establish a therapy based on the anatomical consideration and on the biopsy. But with radiomics, people want to do it much shorter. So you look at the CT scan, and from the features of the image that sometimes you have to detect with artificial intelligence, you can also derive the genetic information on the patient. So you don't need biopsy, you need to wait for weeks to have the results, but you have the information directly from the image. This is a recent example, you see, of the application of radiomics in non-small cell lung cancer, where from the features of the non-small cell lung cancer, from the texture, from this image information, they were able to divide the patients in two groups. In this division in two groups, they find out that they can see which patient is at higher risk and which patient is at lower risk for the lung cancer. Okay, then this is enough for the X-ray imaging. In the next one, we will see non-ionizing radiation imaging.